All right, looking up here, our learning target for yesterday's video was to use Dalton's law to relate the total pressure of a mixture of gases to the partial pressure of each of the component gases. So basically, if we take the partial pressures, we get the total pressure. And I'll explain that a little bit more here coming up. Now, our success criteria are to define partial pressure and describe how it is related to the total pressure of a mixture of gases, to state and recognize Dalton's law of partial pressures, and to use Dalton's law to solve problems involving mixtures of gases. So as I come back up here and I look, talking about Dalton's laws of partial pressure, we see that in this container, I have a little tube here that is running into this bottle of water that's upside down, and it is displacing. This little pink gas is bubbling out of the tube, and it is displacing the water. So I am filling up this bottle with this pink gas, but as I'm filling it up, notice I have these little dots in here also. Well, those are evaporated water particles. So not only do I have the collected gas, but I have water vapor in there also. So I have the pink gas and I have water vapor. Now, to get the total pressure right here, and this is Dalton's law of partial pressures, I just need to add up the two pressures. The pressure here of the water vapor and the pressure here of the pink gas. Now, could I have multiple? Do I have to have two of these? No. I could have multiple. Could I have 5 different ones? Well, yeah. Stop and think of how many gases are in the air we're breathing right now. Okay, so I could have a bunch of different types of gases. Now, for this particular one, I only have the pink and the blue water vapor. Now, here's an actual experiment that we could have done. The decomposition down here at the bottom, the decomposition of sodium chlorate. Now, we did something similar to this in the lab, but we used potassium chlorate. And all we did was we used it to measure and do some calculations. We did not collect the gas, okay? We just did how much oxygen. We took the mass of this right here, then we heated it. We took the mass of the potassium chloride to determine, using the law of conservation of mass, to determine the mass of oxygen. Now, could we have done a similar setup to this? Well, here's the sodium chlorate. We're heating it. As the oxygen gas is released, it's running through this one-hole stopper, it's running down the tube, and it's being collected in this bottle right here. So this bottle is about maybe a quarter of the way filled. Right here is a full bottle, all right? That full bottle has both oxygen and water vapor dissolved in it. So if I were to calculate my total pressure using Dalton's partial pressures, I would have an equation like this. P total is equal to the pressure, the pressure of the oxygen plus the pressure of the water. So if I took the two parts, I could get the total pressure. Well, we're going to use Dalton's laws of partial pressures to make some calculations, okay? So here is the very first problem we're going to be dealing with. What is the atmospheric pressure if the partial pressures of nitrogen, oxygen, and argon are 104.5 millimeters of mercury, 162.8 millimeters of mercury, and 0.5 millimeters of mercury. So what we're going to do, how we're going to proceed with this, ladies and gentlemen, is as follows. We're going to say that the total pressure is going to be equal to all of the partials. So the pressure of nitrogen, the pressure of oxygen, and the pressure of argon. So if I take those three partial pressures, I can get the total pressure. Well, it's as easy as this, okay? 604.5 millimeters of mercury is the pressure of the nitrogen. 162.8 millimeters of mercury is the pressure of oxygen. And finally, 0.5 millimeters of mercury is the pressure of the argon. So if I added those up together, my P total, my total pressure is going to be 767.8 millimeters of mercury. As I go back and look, okay, sig figging it, here's to the 10th, here's to the 10th, here's to the 10th. I'm using addition and subtraction, so I have to have my number to the 10th place also. All right. So my final answer there is 767.8 millimeters of mercury. Now remember, we can have some different types of labels for pressure. We talked about, I had you copy down 4 different gas law constants. One of them was atmospheres, one of them was kilopascals, one of them was millimeters of mercury, and one of them was torr. So we could have different labels for pressure. This one happens to be millimeters of mercury. We're going to do a lab, and I'm going to do a demo lab for you, I think, on Tuesday, and we're going to do some pre-lab stuff on Monday. We used to do a butane lab where we took butane from a butane lighter, okay? So we're going to use that as a simulation, and then I think it is on Tuesday, we're going to do a lab in which I'm going to do the lab, and you guys are just going to take down the data while I'm doing the lab. Now, the only reason that we're doing it that way and you guys aren't doing it is I don't think we have enough time to do it in one period if you guys do it, okay? The setup is a kind of difficult setup, and it's hard to do, all right? So we have to be very, very efficient in order to get it done. So that's why I'm just going to demo it, and we're going to take down the data. But nonetheless, we're going to use some of these partial pressures, okay? Because we're going to have to actually get the temperature of the room in here, okay? We're going to have to actually get the pressure of the room in here, all right? So how can we do that? Well, we're going to end up using the weather channel, because I can look on the weather channel right now and see what the barometric pressure is here in Seatown, okay? Now, what we're going to see on that is it's going to be labeled in inches of mercury because we don't use the metric system here in the United States, okay? So we're going to have to convert that from inches to millimeters in order to use our data. But that will be coming up next week, okay? Here is my second example. My second example says, a 250 milliliter sample of oxygen is collected over water at 25 degrees Celsius and an atmospheric pressure of 101.325 kilopascals. What is the pressure in kilopascals of the dry gas alone? Okay? So what this means, the dry gas alone, okay, is just like we were talking about before. We're collecting oxygen here, but as we collect oxygen, we have water vapor also. So when they say the mass of the dry gas alone, it's meaning the mass without the water vapor. So In this particular equation, we're going to have P total is equal to P of oxygen plus the P of the water vapor. Now, the beauty of this, ladies and gentlemen, is I can rework this equation. I'm trying to find the dry gas alone, which is the P of oxygen. Well, if I rework my equation, I know that the total pressure minus the pressure of the water is going to give me the pressure of the oxygen. So all I need to know is the total pressure and the pressure of the water vapor. Now here's the beauty, folks. I know what temperature it is, don't I? Now you're going to get a chart today. You're going to get a chart today that is somewhat similar to this one. And what this is, I'm looking at, is the vapor pressure of water. And you can see that I have different temperatures and different pressures in kilopascals. So what I need to do, I had 25 degrees Celsius here. So if I look at 25 degrees Celsius, what is the vapor pressure of water? 3.2 kilopascals, right? So if I come back here, okay, and I do my math, 101.325 kilopascals is my total pressure. If I subtract the 3.2 kilopascals, I'm going to come up with a value of, when I did the math, okay, I'm going to do the math to get the total value just to show you the sig figs too. 101.325 minus 3.2, that gave me a value, and I'm going to put that up here in blue, 98.125 kilopascals. Now I come back and I look 3 places to the right of the decimal, 1 place to the right of the decimal. So I am going to round this to 1 place to the right of the decimal to sig fig it correctly. So that's going to give me 98.1 kilopascals. So what is this? What is 98.1 kilopascals? That is the pressure of the oxygen gas. Okay, that is the pressure of the oxygen gas. Any questions? Because that's very, very similar right there to what we're going to need to be able to do for the lab. All right. Now, here is another type of a problem that we could possibly work. And this one says a 32.0 milliliter sample of hydrogen gas is collected by water displacement at 20 degrees Celsius and 750 torr of total pressure. What is the pressure in kilopascals of the dry gas alone? Well, my problem here is that my total pressure is given in torrs, and I want to find the pressure of the dry gas in kilopascals. So I have to do some kind of conversion. So I'm going to take my 750 torr, and I'm going to set up a conversion box, and I've got to have something where torr is on the bottom to cancel, and what am I trying to get it into? Kilopascals. So I need kilopascals on the top. So I've got to find the conversion factor. Now, earlier today I Googled it, and I just said, how many kilopascals are there in 1 torr? And, you know, Google spit out this data for me. Now, I forgot that I'd already put this chart on here. So if I look at this chart down at the bottom, it says that 1 torr is equal to 133.322 pascals. So how many kilopascals would that be? What do I need to do? Well, I just need to jump my decimal point, and if I'm at units, 1, 2, 3 to get to kilo. So 1 torr is equal to 0.13332 kilopascals. So if I take and do my conversion factors back here, I look and I say, okay, 1 torr is equal to 0.133322 kilopascals. So my torrs cancel, and I'm going to get my label in kilopascals, and I need 4 significant figures. So I'm going to take my 750, and I'm going to multiply that by 0.13332, and I get a value with 3 or 4 sig figs, 99.99 kilopascal. So I've converted this into kilopascal. Well, same thing now. My total pressure is equal to the pressure of my hydrogen gas and the pressure of the water vapor. So if I rework my equation, the pressure of the hydrogen gas is equal to the total pressure minus the water. Well, what's my total pressure? 99.99 kilopascals. What's my pressure of water? Well, I have to figure that out. I've got to come back to my data table and find 20 degrees Celsius. So here's my data table. Here's 20 degrees Celsius, and it is 2.3 kilopascals. So I take the 99.99 and I subtract 2.3 from that, and I get a value of 97.69. As I go back and look, 10th, 100th. I can only have it to the 10th, so I'm going to take that 69 and I'm going to round that to 97.7 kilopascals, and that's going to be the pressure of my hydrogen gas. So I could have to throw a conversion in there, and just like I said before, we could have our atmospheres in many different things. Okay, torrs, millimeters of mercury, atmospheres of pressure, and kilopascals, just to name a few. Okay? Any questions on this? All right, good.